This is a continuation of section 5.5, the substitution rule. You should have already attempted these. This is more just showing you the solutions. So for number 9, what works is if you let u be 2y plus 9. When the denominator is linear like this, and there isn't an expression of your variable in the numerator, then this is really just like the integral of 1 over x, okay, or 1 over u. We'll take the 3 out. So du is going to be 2 dy. So dy is du over 2. So we're going to have to multiply by 1/2 to compensate for du. And then we have the integral of 1 over u du. Then this is 3/2 natural log of the absolute value of u, which is 2y plus 9 plus c. Next, if you look at this one, I think the most obvious u to try would be t to the 4th plus 2t, because at least you can see that when you take the derivative of t to the 4th, you're going to get t cubed. The problem is that when you have an expression like this with two terms, your dt had better match it exactly, so or your du had better match it exactly. And in this case, when we take du dt, it would be 4t cubed plus 2. And that doesn't match it exactly, but if you factor, sorry, this is dt. If you factor out the 2, then it does. So dt equals du over 2 times the quantity t cubed, 2t cubed plus 1. And so when we replace this, we've got the 2t cubes plus 1 cancel. And so we just have to factor out a 1/2. And then what we have in our integral is u to the -3 du. Then we integrate. We add 1 to -3, that's -2. We divide by -2. And we have u to the -2 plus c. So this is going to be -1 over 4 times whatever u is squared. Okay, next one. For this one, we can let u be 1 minus 4x squared, and then du is -8x dx, and so there dx is du over -8x, and you can see that the x's cancel, and so then we just need to multiply by -1/8 to compensate for our du. This is our anti-u substitution, or I'm sorry, our anti-chain rule, right? The derivative needs to be divided away, the part that isn't already there. So what we have is the integral of u to the -1/2. Du. And we need to modify by pulling out the -1/8. And then this is going to be -1/8. So if we add 1 to -1/2, we get +1/2. And if we divide by +1/2, we're multiplying by 2. And then u to the +1/2 plus c. So we get -1/4 square root of 1 minus 4x squared plus c. There's our final answer. For number 12, you need to recognize that the integral of 1 over the square root of 1 minus u squared du is, whoops, not inverse tangent, but inverse secant, or I'm sorry, inverse sine or arc sine. Okay. So, and you can see how this form here is modeled. So if we let u squared be 4x squared, then u is 2x. Plus or minus, but of course we're going to let u be the positive 2x. Then du is 2 dx, and dx is du over 2. So when we replace dx, we need to multiply by 1/2. And then we've got the integral of 1 over square root of 1 minus u squared du. And so we get 1/2 arc sine of 4x squared. Actually, I'm kidding. That would be u squared, and it's arc sine of u, not u squared. So I take that back. Or erase might be better. So this should be 2x, and then plus c. Okay, the next one. So this one is maybe a little bit harder to recognize, but recall the integral of 1 over 1 plus x squared dx. This is inverse tangent x plus c. And it might not be obvious, but your first attempt, or what may seem obvious, is to just let this denominator be your u. But then when you take the derivative, when you take du dy, you get 10y, and there's no 10y in the numerator here to absorb that. So you wouldn't be able to change everything over to u if you did that. So this really is this form, but we have to make that denominator look like 1 plus something squared. So let's start with the 5y squared plus 4. And the first thing that we want to do is we need this to be a 1. So we can factor a 4 out. And then we have 5y squared. Whoops, sorry. We have 5/4 y squared plus 1. Okay. So then the next thing we need to do is make that something squared. And that'll be our u, because we can just factor out the 1/4. So our u, or rather our u squared, is 5/4 y squared. So then u can be root 5 over 2 times y. Okay. So now, let me give myself a little bit of room here. So now du is root 5 over 2 dy, and then dy is du. Let's just make it times 2 over root 5. Okay, so we're going to have to multiply our integral by 2 over root 5. Here's our integral. We're going to pull out the 3. We're going to pull out the 4. Okay, so let me write it like this. 3 over the 5y squared plus 4. I'm going to replace that with 4 times the quantity root 5 over 2y squared plus 1. Okay, so I just rewrote the denominator. And then now dy can be replaced with 2 over root 5 du. Okay. So now when we pull out all our constants, we have 3 over 2 root 5. You can rationalize that denominator if you feel inclined. Times the integral of du over root 5 over 2y squared plus 1 du. Whoops, I already wrote du. Okay, and so therefore we get 3 over 2 root 5 times inverse tan of root 5 over 2y plus c. And there's our answer. Okay. Next, we have x times x plus 1 to the 1/2. Okay, so for something like this, because it's a square root, distributing in would require us to square x first. And there's an easier way to do this. I don't think that would work out either way, but that's something you can do too. But normally we would just kind of distribute that, but we can't distribute under these circumstances and get anything good out of it. But what you can do is let u be x plus 1, and then du is dx. And then the problem with that is then we're going to have the integral of x times u to the 1/2 du. The problem is that we haven't converted completely to u. So here's the thing is, since u is just x plus 1, we can solve this for x. X is u minus 1. So we can just replace x with u minus 1. And what we've really done is just switched the order of the distributing. And so then now we're distributing the square root in, and we can do that. So this will be the integral of u to the 3/2 minus u to the 1/2 du. And then that will be equal to 2/5 u to the 5/2 minus 2/3 u to the 3/2 plus c. And then we need to go back to x, which is u is x plus 1. So we have 2/5 times x plus 1 to the 5/2, which you could write as the square root of x plus 1 raised to the 5th power. But this is good enough. Whoops. X plus 1 to the 3/2 plus c. And then one more. So given find r of theta, given that dr d theta is 3 cosine squared of pi over 4 minus theta, with r of 0 being pi over 8. So this right here is what is called an initial condition. And we use it to get c, the constant of integration. Okay, so don't forget to do that. Our final answer shouldn't have a c in it. R of 0 should give us rc. Okay, so we have the derivative here. So if we want r of theta, we just need to take the antiderivative. And so r of theta equals the antiderivative of 3 cosine squared of pi over 4 minus theta d theta. So just remember, every time when you have an integration symbol, a differential telling you which variable is the one that's being integrated needs to come with it. Okay, so to integrate cosine squared, you're going to have to recall one of the few trig identities that really come up a lot. Cosine squared theta is 1/2 times 1 plus cosine 2 theta. That's called a power reducing formula, and we use it every time. That one and the sine one, every time you want to take the integral of cosine squared, it's the way to go. Because it reduces cosine squared to something linear. If you just have cosine squared and you try to let u be cosine, then your du isn't there. Okay, so we can't just do a u sub straight up like that, but we can replace. So here my r of theta equals, we're going to have integral my 1/2 I'm bringing over here, and then I can replace the cosine squared with the 1 plus cosine 2 theta, 1 plus cosine of 2 times pi over 4 minus theta d theta. And then when we integrate this, we can just pull out the 3/2. The integral of 1 d theta is theta, and then the integral of cosine is sine, positive sine of this thing. I'm going to go ahead and distribute the 2. So this will be pi over 2 minus 2 theta times, here's the thing. Okay, so I didn't warn you guys, but hopefully you caught this, that we're doing like a mini u substitution here. So, well, that is too light, so let me pick something darker here. If we let u be pi over 4 minus theta, then du is negative d theta. So we're going to need the -1 to do that, the antiderivative of cosine of that that function, okay, essentially. So that's what the -1 is there for. And plus c. Now remember, let's go ahead and clean this up a little bit, but then we're going to put in 0 and pi over 8, and then we'll have our c. So let's see, so r of theta, make that look a little bit more like theta, equals, I'm going to have 3/2 theta minus 3/2 sine of pi over 2 minus 2 theta. Okay, and if we do r of 0 equals pi over 8, then this term is 0. We get 0 here, so sine of pi over 2. Sine of pi over 2 is 1. This is plus c. Okay, so sine of pi over 2 is 1. So what we get is -3/2 plus c equals pi over 8. And then, so c equals pi over 8 plus 3/2. And so r of theta is 3/2 theta minus 3/2 sine of pi over 2 minus 2 theta plus pi over 8 plus 3/2. And that's it. That finishes for 5.5, and all we have left is the integration by parts.